So, good morning, everyone, and thank you very much for joining today. So, we have another talk for the Kerala Theoretical Physics Initiative. And before I introduce the speaker and get into the talk part, let me introduce the platform itself. So, we are Kerala Theoretical Physics Initiative, abbreviated to KTPI, and we are a bunch of PhD students, postdoctoral fellows, and faculty members across the globe working in theoretical physics and with an ambition to prosper theoretical physics in regional places and all. So we conduct a popular level talk as well as very technical talk in the area of theoretical physics, but not limited to theoretical physics itself. And that is who we are. And today I'm honored to have Ms. Yashi Tiwari with us. And before uh, we begin the talk, let me introduce our speaker of the day. So, Yashi is currently a PhD student at the Department of Physics at Indian Institute of Sciences, Bangalore. She focuses on dark energy modeling and various aspects of modified gravity. So, today we are going to delve deep into the area of dynamical dark energy in the light of emerging cosmological tensions. So, Yashi completed her master's degree from Banaras Hindu University and joined as a PhD student at Indian Institute of Science, Bangalore. And she is about to receive her doctoral degree and soon to be joined as a postdoctoral fellow at the Institute of Theoretical Physics, Beijing. So, without further delay, Yashi, thank you very much for joining today and thank you very much for agreeing to give this talk. So,
Okay,
before
yeah.
we begin the talk, a bit of housekeeping. It is better to ask the question at the end of the session, or you can type your questions in the chat box. I will read that out after the talk, if that is convenient for the speaker as well as everyone else. So, welcome, Yashi. The platform is yours. Thank you.
Okay. Thank you, Manoj, for the kind introduction, and thank you, the organizers at KTPI, to inviting me to talk about my recent work and my topic of research, which is dark energy. So I have the slides number written at the leftmost corner of the slide, if you can see. And if you have any questions specific to some slide, you can ask. I would prefer the questions towards the end of the talk, if that is fine. So, okay, so I think I can start now, right?
Yes, Yashi. Thank you.
Okay. Okay. So, yep. I'll be talking about dark energy. And to begin with, the story of dark energy actually began in 1929 when Edwin Hubble first discovered that our universe is actually expanding. So, what he did was that he was observing the galaxies. Nearby galaxies, and he calibrated the distance to those galaxies, and this distance calibration is something I will talk about later also. It is done using some standard candles like Cepheids or supernovae. And at the same time, he knew the velocities for some of the galaxies. And now, how we know the velocities? So it's like we see the spectral shift. See the shift in the spectral lines that we are receiving from the galaxies, the light that we are receiving from the galaxies. And this calculation of the redshift was actually previously done by Slipher even before Hubble. And this is what Hubble used in his measurement. And so what he found was that he was trying to so if you see this plot on the right corner here, what Hubble did was that on the x-axis it is the distance of the galaxies from us, and on the y-axis is their velocities. And he found that the galaxies were actually moving farther away from us, and the farther the galaxy, that means the more the distance from us, the higher was its velocity. And this was what was given by the famous Hubble's law, which is here, which says that the velocity is directly proportional to the distance. And this proportionality constant here is the Hubble constant, which is named after Hubble, of course, and H naught, which is also a crucial cosmological parameter. It tells about the expansion rate of the universe at present time. So it was this discovery in 1929 which was told that the universe was actually expanding. Before that, we had the notion that the um okay, we had the notion that the universe was static. So now coming back, what do we act how do we actually realize a expanding universe? So it's like, if the universe is expanding today, it means that if you go back in time, it would be shrinking, and it would have started from some really hot dense state. And this is what is the notion of the Big Bang theory, that our universe actually started from a very hot dense initial state, and such a initial state from such an initial state started to expand, and it is expanding till present. And to understand in terms of equations and how we interpret expansion in cosmology is what is indicated here in this right diagram. So you consider that you have some box with size, say, unit length, and this serves as your coordinate system. And as a time increases, for example, this is the situation at some time t1. Now, as time increases, you go to another time t2. This box itself has expanded, and this expansion is characterized by this scale factor. And as the universe, as the time evolves, this scale factor keeps on increasing, and this underlying coordinate system, which we consider it as, so for example, you consider that this underlying box serves as a fixed coordinate system. This coordinate system itself is stretched as a result of expansion, and this can be seen as like physical distances here, like d as a function of time is actually related to the coordinate distance, some fixed quantity, which we say that we have a box of unit length, and this expansion factor. And how this expansion factor actually changes with time. So this expansion factor also evolves with time, and this is what is referred to as the Hubble parameter, which is the rate of change of this expansion factor. In mathematical terms, it's the how fast with time the scale factor changes. So this is what is Hubble parameter, which is a crucial quantity when we are talking about the expansion of the universe. And H naught is actually the present value of this parameter. So this parameter is itself a function of time. And at present time, what is the value of this parameter is what we refer to as Hubble constant. So now another interesting thing happened in 1998. What happened that there were two independent teams who were actually observing type 1a supernovae. I will talk about what these objects are in the next slide. But let's first talk about that what they observed. So they were observing these type 1a supernovae, and from these type 1a supernovae, they inferred the distances to these objects from us, and from those distances, they've got to know that the expansion of the universe is accelerating. Now, does that mean is that before we just knew that the universe was expanding. We didn't knew that whether it was accelerated expansion or decelerated expansion. So if you see this diagram here, so it shows that the universe was expanding in time. But what happened, what these observations indicate is that very recently, this expansion rate is actually quite faster, and it is even, you can say that it is an exponential expansion. So this was something mysterious. Why? Because whatever concept of the universe, the constituents of the universe we had at that point, they were not agreeing with this observation that the expansion is found to be accelerated. And that's why a marvelous discovery, which also got Nobel Prize in 2011. And this was the first evidence that there is something non-trivial, something fishy that we don't know about. And because we don't know about it, we call it a dark energy. And it is something which has some repulsive force to counteract gravity, because gravity is always there to hinder the expansion. And if something is expanding that too at an accelerated rate, it means there is a strong force, strong repulsive force to counteract gravity, and that is what is referred to as dark energy. And in mathematical terms, it is known as that it can be written as the second derivative of the this scale factor. The expansion scale factor would be positive. So now, just before going further, just a quick overview of what these objects type 1a supernovae are. So these are some powerful explosions which happen in a white dwarf, which is a stellar remnant, and when in a binary system. So what happens is that this white dwarf is a very hot and which is a very dense object, and when in a binary system, it accretes mass from the companion star, and whenever it reaches a critical mass, whenever the mass reaches around 1.4 solar masses, which is also called the Chandrasekhar limit, there is a thermonuclear blast that happens. And this is very well worked out astrophysics, and this mass limit is also known as Chandrasekhar mass limit, and which leads to some particular amount of energy released into the interstellar medium. And that's why these objects are known as standard candles, because we have worked out that when this particular mass range would be reached, there would be a thermonuclear blast of this given energy. So they have a nearly uniform peak luminosities. And because of this, they are referred to as standard candles. That is, we know some of their intrinsic behavior. Now, how they are used to infer distances. So what we do in astrophysics is that we are observing some object. For example, we are observing a supernovae at some redshift. When I say redshift, it's like I am looking back in time. So when I am observing some supernovae, we are actually observing their apparent brightness or their flux. And if we know their intrinsic luminosity, their how much energy they would have actually injected because of the known astrophysics, we can infer a distance to them, just relating the flux to the luminosity. And in astronomy, this is given by this particular relation where small m represents the apparent magnitude, that is some observed flux, whereas capital M is the absolute magnitude, and it could be calibrated with the known astrophysics. And by observing this apparent magnitude and doing this calibration, one could get an inference of distance, how far that object is. Now, this distance calculation is very crucial in cosmology, because it tells us about the underlying model, that what is the constituents of the universe, whether it is dark energy, dark matter, or what. So this is what is how the supernovae are used for cosmological inferences. So here is a diagram this is a plot where this red points are the data points. So on the x-axis, we have the redshift, and these data points are the supernovae that we observe. And this is the effective apparent magnitude, which has the information of the distance. So it's like you have an information of distance to different supernovae at different redshifts. And whenever you have a relation between distance and redshift, you can constrain the underlying cosmological model, because the model connects the distance to the redshift. Now, what these observations in 1998 indicated is that at that point, we did not know that there is any dark energy. So the theoretical models that what we were trying to fit with this data are these, where this is with the blue dashed lines. If you see them, so these are the models where there is no dark energy. So we found that these models indeed were not giving the good fit to the data, and only when you have some component which is accelerating, for example, dark energy, then only this data could be well fitted. And this is how we inferred that there is indeed something called dark energy, which uh, only we can incorporate the distances to these supernovae, which appear to be um, out there in the universe. Now, yeah, at this point, if someone is not aware of what redshift is, so redshift is just a measure of how much the wavelength of a light has stretched due to expansion. And it is related to the scale factor as inverse. So it's like in the very early universe, when scale factor was very small, that means you are looking at very way back in time, so high redshifts. So whenever I say high redshifts, it means in way back in the past. Whereas at present time where we live, we call it at a redshift of 0. So this is how the supernovae observations actually discovered that the universe is indeed accelerating and we need a dark energy. So this is the story of how dark energy was first discovered. Now I'll come to what is the standard model of cosmology. That is what the community has settled upon in recent years. So in the last 20 years, it's the standard model of cosmology is the lambda cold dark matter model. It is a 6-parameter, very simplest model. To start with, it is based on two key ingredients. First is the cosmological principle, which says that if you look the universe at very large scales, cosmological scales, then this appears to be homogeneous and isotropic. So there is no preferred direction. If you see this underlying image, which is from a large scale structure survey, you see that there is no preferred direction and it looks the same in all the directions. And what this principle gives us is this resolves a metric for the universe, which is homogeneous and isotropic, often referred to as Friedman Lemaitre Robertson Walker metric. And these metric, so it indicates that there is no preferred direction. So if you see this spatial vector, so it is expanded the same way in all the directions, incorporating homogeneity and isotropy. And this metric contains very crucial information for distances and also the geometry of space-time. Now, the second ingredient that you need is how the geometry of space-time will actually change in a universe depending on the contents. And this is, for this, you need a theory of gravity, for which the standard model works on Einstein's general theory of relativity, which relates the curvature of space-time to the energy content of the universe, which be it matter, radiation, dark energy, or dark matter, and how it changes the geometry. So with these two ingredients together, so this is the metric of the universe, which is homogeneous and isotropic, and then combined with the Einstein's general theory of relativity, we study the cosmology, standard model of cosmology. So what the scenario is that our universe is expanding. There are particles, matter, radiation inside it, and the expansion rate is actually changing with time. And this is what is given by the Friedman equations, which are actually obtained from the Einstein's equations. So the first Friedman equation is something which tells how this expansion rate, which is the Hubble parameter, the same parameter that I discussed in the initial slide, now in terms of these equations. So this parameter, how it is related to the total energy density of the universe, where this rho is the total energy density, which has contributions from different components. And with time, this energy density will also change. Why? Because the universe is expanding. Now, for different fluids, we can model different fluids with the equation of state, which relates the pressure to the energy density of the fluid, and the conservation equation of the energy density in an expanding background is something also mentioned here in this equation. And you see that for W, which is, say, less than -1, all these quantities will always dilute with time. So it's like, yeah, did I say it right? Yeah. So for most of the quantities, apart from some exotic quantities like phantom, which I will talk about in the later in this talk, most of the constituents like matter and radiation, the energy density dilutes with time. Why? Because the universe is expanding. Now, the second Friedman equation is something which tells about the scale factor, the double derivative of the scale factor, which encodes information whether the universe is accelerating or decelerating. So if you see this equation and you see that the condition that requires that the scale double derivative to be positive is that this equation of state for such a fluid should be less than -1/3. So this is a mathematical construction to understand what is the requirement of any fluid to explain accelerated expansion. And I'll show later that why the known components like matter or radiation could not explain this, because this particular condition was not satisfied. So what are the contributions to the energy density of the universe that we know? First is the radiation. We know that we observe the cosmic microwave background radiation, which is the relic radiation from the early universe. And this is very homogeneous and isotropic. It has very small fluctuations of the order of 1 in 10 power to 5. And being a radiation, its this energy density and pressure are related by this, that the equation of state is 1/3. And its energy density falls as universe expands as 1 over A4. Now, the other component is the matter component, where there are two parts. One is the baryonic matter, whatever we see, but most of it, like 85% of the total matter, is the cold dark matter that we don't see, but it is there. And it, because of, and if it would not have been there, we would not have seen the large scale structures, the galaxies distributions that we see today. So which itself is a separate topic of discussion. But for today's talk, I'll just mention that the matter content, we have baryonic and the cold dark matter, and they are assumed to be pressureless. They don't have pressure, so that the equation of state is 0, and their energy density just dilutes like a volume factor, 1 over A cube. However, recalling from the previous slide where we see that the accelerated expansion corresponds to equation of state which is less than minus one third, you can see that any of these components cannot give you this accelerated expansion which is actually observed. And that's why there is a need of another component. We don't know much about it, but we call it dark energy. So what is dark energy? So it is a fluid which satisfies this condition, which is that equation of state is less than minus 1 by 3. And this minus sign indicate that this is some quantity with a negative pressures, given that W is P by rho. So this negative pressure is something which counteracts the attractive force of gravity and leads to a faster expansion. The more the negative pressure, the faster the expansion. Now, in standard model of cosmology, this dark energy is actually very nicely accommodated by a cosmological constant, which is just a constant. Constant means its energy density remains same throughout. So if you go back to the expression where we see the how energy density evolves with scale factor as the universe expand, if this equation of state W here is minus 1, we see that this rho is actually a constant. It does not evolve in
Yes.
time. Yes.
Hi, Yashi. Can you hear
Yes.
me? So there's a question in the chat box. They are
Uh,
asking that can you explain how the second derivative of the scale factor corresponding to some way to the dark energy by Sahel?
so it okay, so if you see this equation here, you can see that this A double dot by A, now here rho is sitting, rho energy density is always positive. So in this setup, you see that for A double dot to be positive means A double dot positive means it, um, can you hear me? I see internet connection is unstable. Hello?
Yes, we can hear you, Yashi.
We can hear you.
Hello? Oh, okay, okay, okay. Okay, okay. Okay, I just turned off my video to save the bandwidth because it shows internet connection is unstable. So returning to the question, yes. So double derivative of the scale factor actually tells whether the expansion is accelerating or not. And for accelerating, we need a positive double derivative. So from this equation in mathematical terms, you can understand that this condition is only met when this 1 plus 3 omega is also negative, so that this A double dot becomes positive because all the other quantities otherwise are positive. And this leads to this condition that equation of state is less than minus 1 by 3. So I hope it is clear from this point. So, okay, I will then go further. Yeah. So so that's why we need a dark energy, because we don't have any fluid that we know which satisfies this condition. And in standard model of cosmology, a simple cosmological constant lambda actually does this job very nicely. And this says that the energy density of the dark energy remains constant, which means that its equation of state is minus 1. Of course, W equals to minus 1 satisfies this condition that W less than minus 1 by 3. So the picture of the universe is something as shown here. So we have three major components in the standard model. One is the radiation, other is the matter, and the third one is the dark energy. Now, the radiation and matter, their energy density actually dilutes with time. So as you go towards the right, so here the scale factor increases. That means on the rightmost, we are talking at present time, whereas at the leftmost, it is very early in the universe when the universe was very small in size. Now, as expansion happens, the energy density of radiation and matter fall. Radiation falls faster because of the 1 over A4 scaling, and matter falls comparatively slower. At some point, they are same. That is called the matter radiation equality. And later on, matter becomes a dominant component. And very recently, this becomes significant enough to contribute to the universe accelerated expansion. And this is how the energy constituents of the universe actually control how the scale factor would evolve at different times. At initial times, it would be dominated by radiation. The late time expansion would be dominated by matter, whereas very presently, when the energy of the when the dark energy density is significant enough in comparison to matter and radiation, it becomes to dominate the present accelerated expansion. So this is our concordance lambda cold dark matter model, the standard model, where lambda stands for dark energy, CDM stands for cold dark matter. Both of these components are actually the most dominant component. If you see the energy budget today, which is shown here in this cosmic pie chart, you see that the dark energy corresponds to 68% of energy, whereas the cold dark matter is around 27%, and whatever ordinary matter that you see in forms of stars and galaxies, that is less than 5% and very small amount of radiation. Now, the expansion rate in the standard model is then given in terms of these components: matter, radiation, and dark energy. Matter and radiation, they both are function of redshift. That means they vary with time. They are diluting slowly because of the expansion, whereas lambda is just a constant throughout. And there is this notion to describe the critical density, which is the density at which universe is spatially flat. In this talk throughout, I have assumed a spatially flat geometry, which is something which is also very well confirmed with the observations. So this is just for the notations that now the Hubble expansion rate could be given something as follows, where these omegas are actually the ratio of the different densities for matter and radiation in comparison to the total density at present, to tell you the budget of the which quantity constitutes most of the component at present time. So here we have these cosmological parameters, H naught, which is what you already know. This is the present Hubble constant, and then omega m, omega lambda are the quantities which tell you about the percentage of the energy budget today for the different components. Now, what we do in cosmology, that what we are trying, we have built a model. Now we want to confront the model with the observations, see whether the model is actually giving a good fit to the observed data or not. And for this, we have plenty of observations. Firstly, the background evolution means we are looking at how the expansion rate is evolving with time. And what this expansion rate has in it, it has information of how distances would be calculated in an underlying cosmology. So when you have expansion rate, you can measure the distance at a given redshift. And then we have a lot of observations, particularly, for example, at the background level, we have baryon acoustic oscillations. This is something I will talk about later in talk. Type 1a supernovae, I have already discussed that we are observing the brightness of these supernovae, and knowing their intrinsic brightness, we can get an estimate of how far they are. And whenever we have a distance measurement in cosmology, we can translate it to expansion rate. What is the underlying expansion rate, and constrain the different cosmological parameters. So this is the background evolution, which the observations which tell us about that there is around 68% of dark energy, without which we cannot reconcile these observations. Now, but this is not all. In what we do in standard cosmological model is we study the perturbations as well. Why? Because the universe is homogeneous on very large scales, but at small scales we see inhomogeneities, even the structures and in fact planets, stars, and we would not form if the universe would be homogeneous and isotropic. So we have to study these small perturbations on the top of a homogeneous background, and how these perturbations evolve to form the large scale structures that we see today. And this is indeed a detailed analysis, and we have very nice data from the CMB, the cosmic microwave background anisotropies, the small fluctuations that I talked about, like 1 in 10 power to 5. And we have a measure of these anisotropies, as well as we have measure of the matter over the energy matter perturbations. And these observations together also are very well explained by the simple lambda CDM model. I will not go into detail of these analysis, just to give an overview that there is a standard model which has 6 parameters. It is based on 3 key ingredients. First is the dark matter, then is the dark energy, and also we need a phase of cosmological inflation to explain the origin of the small perturbations in the universe. So, but for today's talk, what we are interested in is the dark energy, which is one specific component of this model. And for this, we are just interested in the parameters which tell us mostly about most information about the dark energy, like omega lambda. So for example, in the case of lambda CDM model, where we have seen that the dark energy is just a constant throughout with the equation of state -1. What we do is that we take different cosmological observations. For example, this is the CMB sky. This is the observations from the anisotropies of CMB, where the different colors indicate the fluctuations in temperature from the mean temperature. And these fluctuations are really small, like of order microkelvin, when the mean temperature is of the order of Kelvin. And then we have large scale structures where surveys where we are actually mapping the distribution of galaxies. And this distribution of galaxies encode very crucial information about what are the ingredients of the universe. For example, if there would have been no dark matter or no dark energy, this distribution would not look like what we observe. So these are also indirect confirmation of the different constituents of the universe. And then we have observations from supernovae, again, that we have discussed. We observe their apparent brightness and compare it with intrinsic brightness to get a distance. And we combine all these observations to see that whether our standard model is able to provide a good understanding to all of them at the same time. So you see that it's like we sample over the cosmological parameters omega matter and omega lambda and try to see that what are the best fit values of these parameters, which are well incorporated by all the observations. And you find some best fit constraints indicated here, where you find that the omega lambda is 0.68, means 68% of the energy budget is contributed by the dark energy, whereas matter contributes to around 30%. So yeah, so this was the case of constant dark energy, which is lambda CDM model. But phenomenologically, one can also think that what happens if dark energy is not just a constant, and rather it could vary. So what if dark energy is evolving? Then the expansion rate would change. First thing is this. So how? So it's like, this is how, from the energy conservation equation that I showed in the initial slides, the energy density of dark energy would vary if the equation of state was something other than -1. So if you see here in this equation, if the equation of state is not -1, this integrand would be non-zero, and indeed the dark energy would be a function of redshift. And that is what we refer to as dynamical dark energy, or DDE if I use further in the talk. So whenever the equation of states departs from W equals to -1, we have dynamical dark energy. Cool. Then how to model such a dynamical dark energy? So two most interesting model that are used, studied in literature is that, for example, now you say that, okay, the equation of state is not -1, but something else. So that cosmology we call W CDM cosmology rather than lambda CDM. Lambda means W equals to -1, whereas W CDM means W is free to have any other value. In such cases, now the expansion rate of the universe changes, particularly the third term where the dark energy comes into picture. Yes, this is not a constant, but this also evolves with time. And here you have got one more extra parameter in the picture, because in case of lambda CDM, that's why it's a simple model, because you have fixed W equals to -1 and a constant is just doing the task. Now you have a evolving W, where W itself, you have a W which is other than -1. Of course, W is a constant, but now you have to, this also becomes a parameter in the theory. So you have one extra parameter, W. What else can be done? Now you can say that let's go a step further, and W itself could also evolve with redshift. That is what, there is an evolution in the equation of state. So for example, a well-studied model is the CPL parameterization, where the equation of state at present time, that is at Z equals to 0, is W naught, whereas it can vary with the redshift as given in by this equation. And again, because now in this case, you have two parameters, W naught and WA, this becomes a further extension of from the standard scenario where you have two parameters, and the expansion history would again be a bit complicated in comparison to the standard one because of the evolving W. Now, this was the case when we are just parameterizing without thinking that what could be the origin of such a fluid. So in cosmology, we work a lot with the scalar field, and scalar fields are can be good candidate to explain dark energy. For example, studied model is the quintessence dark energy, where the scalar field could be minimally coupled to gravity given by this Lagrangian, where there is a kinetic term in an expanding background because of the metric G mu nu, and there is a potential term. And For this particular Lagrangian, you can work out what the energy density and pressure would look like. And the equation of state, which is pressure by energy density, could then be given as follows, where phi dot square, half phi dot square is the kinetic term, and V phi is the potential term, and the total energy density is sum of kinetic and potential. What interesting phenomenology it brings is that depending on the choice of potential and the this amplitude of the kinetic term, you can have different scenarios. You can, for example, if the kinetic term is very small in comparison to the potential, the equation of state will just become close to -1. You can ignore this phi dot square in the numerator and denominator, and this will give you a similar dynamics like lambda in the lambda stereo model. However, if the phi dot square itself has some sufficient amplitude, then the equation of state could be something else other than -1. So this gives you a phenomenology to model such type of parameterizations that I discussed in the previous slide from a Lagrangian perspective using a scalar field model of dark energy. Then there are other non-trivial models of dark energy as well, which I will not talk as of now, but yeah, there are plenty of them. Now, the important question to ask at this point is that why do we need a dynamical dark energy? Why we are not happy with the simple cosmological constant? So the answer is that firstly, there are emerging tensions. So this is a very new and very hot field in cosmology these days, which is called cosmological tensions. So what these tensions are, so these are some new challenges that are appearing. Why? Because now we have a lot of observations which are seeing the universe with very precision, very good precision and accuracy, and with a lot of data coming up, we are getting measurements of some cosmological parameters which are actually mismatching with our theoretical predictions based on the standard model, and that's why we refer to them as tensions. Now, to explain what tension is in terms of in statistical terms is, for example, it's a discrepancy between two measurements. So it's like you are trying to measure some parameter, say Hubble constant, and you're using two different observations and you're getting very different values from them. What it means is that, for example, you have two observations which give you a measurement x1 and x2 with some uncertainties sigma 1 and sigma 2. And if to illustrate, if I plot a probability distribution function for these two observations with their mean values and their sigma. For example, here I have used H naught from one measurement, which is Planck, and the other measurement, which is shoes. And one gives a value around 64, 67. Other one gives a value of H naught around 73. And they have some uncertainties. You see that these probability distribution functions don't overlap. That means these measurements are not consistent with each other. How to quantify the intensity of this discrepancy? There is this term used, significance, which is defined as the difference of these mean values that you're observing over the combined error propagated in such an analysis. And if you plot the PDF for such a difference, you see that this is deviating from 0 by greater than 5 sigma. So it's like if these observations were consistent, x1, x2 should be very close to each other. And if you plot the probability distribution for the difference, it should be very close to 0. But we find that these values are really inconsistent. And the severity of tension is given by the significance. So if this value is less than 2, then it is a weak significance. Otherwise, if it is greater than 3 sigma, it is considered to a strong tension. To illustrate when it is a strong and when it is weak, I have included here another measurement of H naught from a third observation. So we see that this third observation actually overlaps with both of them. So it's like it's not in tension with any of them. However, the first two, the blue one and the black one, are really in tension. Now, coming back to the question that we asked, that why we want to explore dynamical dark energy, and that's because of the tensions. Tensions, we understood what we call as tension in cosmology. Now, these are three of the motivations that I will talk about today for the need of the dynamical dark energy. First one is the Hubble tension. Second is that we are getting some hints that the dark energy is indeed dynamical from a recent observation, which is dark energy spectroscopic instrument. And third is a even deeper question about the nature of dark energy. which I will, if time permits, I will talk about it. So firstly, I will talk about the Hubble tension. So as I mentioned that this H naught is a very crucial cosmological parameter, first named after Hubble. So it's the present expansion rate. And there are two measurements which are very strong disagreement with each other. So one is the early universe measurement, and this early universe measurement are based on the cosmic microwave background anisotropies. And this measurement gives a value of H naught around 67. And this measurement assumes a model of the universe. So there is an information of the model of the universe going in this measurement, which is the lambda cerium model. The other measurement is more of model independent, and it relies on these distance ladder techniques, the similar which was used by Hubble to calibrate distance to nearby galaxies. And this gives you a value around 73. And in this diagram is shown how this tension has actually, so on the y-axis is the value of H naught, and on the x-axis is the years. And with passing years, we see that these two measurements have actually moved very far away from each other. The red one is the CMB measurement, which gives the low value of H naught, whereas the blue one is the high redshift, is the high value of H naught obtained from distance ladder. Now, just to give a slight overview of how measurement of H naught is done in early universe. So in early universe, we are observing the CMB. So CMB, so it is what happened in very early universe was that when it was very hot and dense, the photons and the baryons were coupled to each other. But as universe expanded, this coupling decreased, and at a point reached around a redshift of 1100, also called the redshift of recombination, where the CMB photons, the photons firstly free streamed. They were not talking to baryons after that. And that is what we see in the CMB observations.
Madam,
And
can you explain what is sound horizon?
yeah, I can explain that. So what we are actually measuring here is this parameter theta, which is the angular size of the sound horizon. So the sound horizon is actually the distance traveled by the photon baryon fluid before recombination. So from the start of the Big Bang till this epoch, when the density became so diluted that the photons traveled free streamed, leaving the baryons, the distance, it was the distance traveled from that point of Big Bang till the recombination. So this is what is known as the sound horizon. So it is like a standard ruler. And I will tell you in later slides as well how the standard ruler is actually very helpful in understanding about the expansion history of the universe from baryon acoustic oscillation observations. So
Thank you.
yeah. So what we are measuring actually is this angular size of the sound horizon. So as I already told that the sound horizon is some standard ruler, we know this object, and this has a characteristic length, and we are observing this angular size of this in the CMB. Now, that means this angular size could be given as the size of this sound horizon over the distance. So distance is from observer, where we are the present observer, and distance is calculated from present time to that last scattering surface. So here you can consider that this quantity theta is actually very precisely determined by cosmic microwave background. And this also is a characteristic length scale. So the thing is the denominator d, where the distance calculation involves and where the dark energy model will go into picture. Why? Because we
So,
are
madam,
calculating.
you are saying that the sound horizon can be I mean, evaluated from the CMB radiation pattern.
This theta can be this theta is what is observable. I'm saying that sound horizon can be calculated using some standard physics, that before that in the very early universe the photon and baryons were tightly coupled. So this is something which could be treated as a standard ruler for the
Okay,
sake of
okay.
yeah,
Thank
that's what. Yeah, and this distance capital D is what we are measuring, this distance from present to that surface of last scattering. So it incorporates the late time expansion history. That is what is your model of the universe, whether it is lambda cerium model of dark energy, or it is W cerium, or some other WZ evolving dark energy quintessence or whatever. So and so that's why H naught here is a derived parameter. So it is obtained from this calculations. We are not directly observing H naught, we are observing this theta, and H naught is derived here and is encoded in this distance measurement. So the next thing is how this was how H naught is inferred from early universe. Now let's talk about the late universe. What we are doing again, we are looking at the standard candles, the method that was first used by Hubble. So we are looking at some standard candles like Cephids, which are some stars whose luminosity actually varies in a definite, in a certain way with the time. So and we use these Cephids to go further into the to look in the faraway galaxies. And in the local universe, you can find the distance using parallax method. Whereas when you go to higher redshifts, you cannot do that. So you use, that's why you rely on the standard candles. And because of the standard candles, you know some of their properties. So observing their flux and knowing their intrinsic properties, you can get an estimate of distance. Now, once you have the distance, and on the other hand, you have the velocities again coming from the redshift measurements of the seeing the spectral lines of these galaxies redshifted in the, you get an estimate of their velocities. And when combining distances and velocities in a Hubble's law, you get an estimate of H naught. So this measurement is more of model independent. Now, you have understood that there is a tension. The two measurements, one arising from a theory prediction of lambda CDM and other arising from distance ladder techniques, don't match. What we try to do, we try to resolve this tension by, so there are various ways of resolving tension. I'm just discussing one particular perspective, which is using dynamical dark energy, DDE. So when we are saying that we want to use dynamical dark energy to resolve tension, what we want to do is, the aim is that we now want to modify the lambda CDM picture. We say that, okay, instead of lambda, we have something else, which is non-trivial. And we want to get a large value of H naught, which is consistent with what is observed by the distance ladder measurements. However, the catch is that you cannot disturb the CMB observations, because CMB observations are the most pristine observations in cosmology, and lambda CDM model gives a really a very good fit to this observation. So whatever extension of lambda CDM that you bring into picture, it has to be such that the other observations are not disturbed. So that means this makes the things very tricky, that you have to modify the expansion history such that this distance to the last scattering surface is not disturbed. It remains unchanged. So one very rough way to understand what one can do is that, for example, instead of lambda w equals to -1, you can have some other equation of state which is constant, and the expansion rate would then be given by this. However, the distances cannot change. So, and you want to increase H naught. So increasing H naught actually demands that the equation of state of dark energy should be less than, 1 plus W should be less than 0. And this is the famous phantom dark energy that people talk about. So phantom means the equation of state is less than -1. What in mathematical terms, what in physical terms it means, it leads to a faster expansion in comparison to lambda. So the equation of state is P by rho. If the equation of state is less than -1, it means the amplitude of the pressure is more than that of energy density. It's like it's more negative pressure, and higher the pressure, negative pressure, faster the expansion would be. And to get a large value of H naught means you need a faster expansion. So this is a physical intuition to understand what is a phantom behavior. So yeah, so it's like you have a phantom equation of state, you can get a large H naught. But the problem is there are various other observations like baryonic acoustic oscillations, which get disturbed when you use these simple tricks to fix a large value of H naught. And that's why we need something really non-trivial, that is some evolving dark energy to explain the Hubble tension. Evolving dark energy means arising from an evolving equation of state to explain the Hubble tension. And there are various works done in the literature. I will not give a detailed analysis of those, just a broad overview that these works have tried to understand that what dynamics this equation of state should have in order to reconcile the cosmological tensions. And it has found that sometimes when the dark energy has features like phantom crossing, phantom crossing means the equation of state resides sometimes in the phantom regime, that is W less than -1, and other times in the non-phantom regime, and there is a crossing between the two. So there is an evolution in equation of state such that it is phantom and non-phantom both at some epochs. So this is phantom crossing. Then there are also features studied like negative dark energy density. If the energy density of the dark energy is negative at some times. So these are some non-trivial features. And also there is variation in the gravitational coupling constant, G effective, which otherwise we think is a constant in our GR and Newtonian theory. But if this could vary, then we could give explain the cosmological tensions that are present today. Now the question arises that how to model such a theory, because these non-trivial features that you observe, like that you talk about, like phantom crossing or negative dark energy density, these cannot be accommodated in general relativity framework without pathologies. So these leads to some theoretical inconsistencies in the theory, which cannot be uh, le- cannot lead to a well-defined theory. So that's why people work with modified gravity theory or some other extensions of lambda cerium like interacting dark energy or dark matter to incorporate such non-trivial dynamics. So here I will just highlight one of my work where we modeled a particular dark energy dynamics to obtain a to understand if we can solve the Hubble tension. So you see that this is the plot for the evolution of Hubble parameter, and this black one is the lambda cerium, which gives you some 67 value, whereas the colored ones are the model where we have used some non-trivial dynamics in a modified gravity framework to explain a large value of H naught at present. But it comes with a cost of some really um, um, difficult dynamics in equation of state, where the equation of state has a weird evolution in redshift. And we have shown that such type of dynamics actually cannot be incorporated in a general relativity framework. So this was the first part where I discussed about the Hubble tension, that if you want to solve Hubble tension with late time solutions, you need a dynamical dark energy. Simple lambda is not able to explain the Hubble tension, and that was the first motivation for the dynamical dark energy. The other one is that we are getting some hints of dynamical nature of dark energy from DAISY. So what is DAISY? This is a dark energy spectroscopic instrument. This is a ground-based telescope which has observed around 15 million galaxies and quasars in the redshift range, like 0.1 to 3.5. It is in Arizona. And now let's talk about what this observation is. So before going further, what DAISY is actually observing, so it is measuring the expansion history at different redshifts, which helps to us to constrain the cosmological model or the dark energy properties. Now, how this expansion history is actually measured by DAISY, this is by the phenomena called the baryon acoustic oscillation, a slight overview of which we talked about in case of sound horizon. So what is happening in short, when the universe was very in the initial stage, it was hot and dense, and the photons and baryons were very tightly coupled with each other, and they were behaving as a single fluid and undergoing oscillation. So then what happened, that as recombination at approach, recombination means an epoch where the energy density of the universe was so diluted that the photons begin to free stream, leaving the baryons there itself. So at that point, the baryon just stalled wherever they were left. So this is just a pictorial representation of what BAO would be in the first left diagram. So it's like after the photons left, the baryons just stalled there, and that's why it left a characteristic scale in the underlying distribution of the galaxies. What happened later on, a lot of galaxies formed, and the large scale structure, the actual large scale structure looks something like the middle figure, and where this information about this characteristic scale is actually deeply hidden inside it. You cannot see such type of feature in a large scale structures, because a lot of galaxies and structures have formed to hide it from us. So how to extract this information? This information can be extracted in a statistical way, like you find 2-point correlations with, for example, you find how many galaxies are separated by a given distance. You find the number count of such galaxies, and usually it follows a Poisson distribution. But for this particular length scale, which is hidden inside the large scale structure, so where you see a bump suddenly, that which corresponds to this baryonic acoustic oscillations. So this is what baryonic acoustic oscillations is. Now, what observations are doing? So in the correlations of these galaxies, you see a bump at some particular characteristic length scale, um, which is the length scale corresponding to the sizes of these acoustic features. And you are measuring again a theta, which is an angular distance to the angular size of these objects. And you know the size of these objects because from the early universe physics. So it's like you have a standard ruler whose size you know, and you're observing their angular size. Now you can constrain the distance to them, which is the angular diameter distance to these objects. And whenever again you have distance, you get a measurement of expansion history. So wherever you get a measurement of distance, you can constrain the underlying cosmology. So this is how baryon acoustic oscillation actually constrains the expansion history. So now coming back, what this observation is actually telling. So this observation tells that the models where the equation of state of the dark energy actually evolves with redshift, they are giving a better fit to the data. So in comparison to lambda CDM, particularly they talk about the CPL parameterization, the W0 WA, which I talked about in the earlier slides. So with this particular cosmology, they find that the data is very well fitted in comparison to lambda CDM. And in fact, this is what is illustrated in this diagram, the middle diagram, where the best fit constraints on W0 and WA are given. And this dashed lines, this particular point corresponds to, this corner point corresponds to the value of W equals to -1 lambda. And you see that this point is not incorporated. This does not match with the um, constraints obtained in the W0 WA plane from the data. And it says that this lambda CDM is actually not doing good in comparison to these evolving dark energy models. And here is a better illustration. This green line shows that how, according to these DAISY observations of baryon acoustic oscillations using the best fit values, how the equation of state actually evolves with time. So you see that there is an evolution with redshift. Z is given on the x-axis. So this is high redshift. So you see that, and this W equals to -1 line is what is the lambda. And however, the best fit gives you an evolution something like this. And you see that at high redshifts, this behavior resides in the phantom regime where equation of state is less than -1. Whereas at late times, near the present time, it goes to equation of state greater than -1, which is a quintessence type of behavior. So you see that there are this evolution in dark energy, which cannot be explained by the lambda CDM. So you need to go beyond lambda cosmology. Also, what is interesting is that you see a phantom behavior at high redshifts. Now, again, as I mentioned earlier, in general relativity, this phantom behavior of equation of state comes with a lot of instabilities and unphysical theory. So to understand what type of theory could actually give you a dynamics which gives you an evolution in equation of state like this, which is preferred by the observation, you need to maybe go to a modified gravity theory where such features can be accommodated without instabilities. So this is the another motivation that why we need dynamical dark energy, because the recent observations has hinted towards this particular behavior and even indicated that it could be having some features which cannot be explained by the general relativity. Now, the third one is testing the nature of gravity on cosmological scales. I will just very slightly talk about it. So it tells us whether it probes the nature of dark energy even at a deeper level. So at right now, what we have talked about is just at the background level. We are looking at the expansion history of the universe and trying to constrain the dark energy properties. But if we say that dark energy is arising from a modified gravity, then it can have very distinct signatures in the growth of perturbations, in the growth of structures that we see today. And looking at these observations, we can distinguish the effect of general relativity or a modified gravity dark energy. And this would even further broaden our understanding of whether dark energy is something like lambda or something else, or it needs a modified gravity theory to explain dark energy. So, and these are the three prime motivations. And now I'll come to modified gravity, which is actually also my topic of research. So why modified gravity is a promising avenue? I'm not saying that modified gravity is the only solution to model such a dynamical dark energy, but this is one promising avenue. Why? Because such theories can very easily accommodate features like phantom crossing, where the equation of state could transit between phantom and non-phantom behavior, sometimes negative dark energy as well, and variation of gravitational coupling. And these things can be done in a modified gravity setup without introducing instabilities in a viable theory. Now, there are a lot of modified theory gravity theories. This is just an illustration of how they are classified. However, I'll just talk about Horndeski theory, which is something that I have personally worked upon in my PhD projects. So this is a very simple extension of general relativity. So in general relativity, what we have, this is a general relativity is a theory where the Lagrangian is just constructed out of the metric tensor. However, if you want to go beyond general relativity, you have to you can introduce the simplest ways to introduce an extra degree of freedom, which is a scalar field. Now, this theory, which was given by Horndeski. So this Horndeski was actually Lovelock's grad student, and Lovelock gave him a task to write a Lagrangian in 3+1 dimensions, such that equation of motion are always second order. What happens sometimes you go to a MG theory or higher dimension theory, you stuck with equations which are greater than second order. However, Horndeski made this Lagrangian in such a way that it includes all the interaction terms between a metric and a scalar field. So the Lagrangian is composed of a metric and a scalar field, and such that the equations always remain second order. So this is a very beautiful theory. And what is interesting is that this theory incorporates various other subclasses like non-minimal coupling of gravity, non-minimal derivative coupling. Even simple GR could be incorporated in this complicated setup by carefully choosing these coupling functions like G2, G3, G4, G5, etc. And that's why this is a very interesting class of theory. And just for the fun fact, so Horndeski, after doing his PhD, he got interested in paintings, and he has indeed become a successful painter. Here is one of his paintings with his equations written on that. So yeah, with this, I will just show this slide where that what I have done in my research work. So I have mostly explored this Horndeski theory and different interaction terms. So if you see that there are different terms in this interactions, and I have explored some different terms of these interactions in context of some tensions and anomalies in standard cosmology. In my first project, I have explored these Horndeski theory in context of inflation, cosmological inflation, to understand some CMB, some anomalies, some problems, some data points which are not explained by standard model in the cosmic microwave background. Then in the later projects, I have worked on Hubble tension, modeling a solution to Hubble tension in Horndeski gravity, the plots, one of the plot that I showed in the previous slides. And also how these non-trivial dynamics will actually have effects on the growth of structures. So it's like going beyond the background level and seeing that if we have a dynamical dark energy with these features, how it will affect the growth of the structures. So these are my collaborators. The rightmost is my research supervisor, Rajiv. This is Nilanjan, who is my senior. Basundara, again, a senior. Ujjwal is a junior who is also doing PhD at ISC. And yeah, now with this, I'll just come to my final slide, the takeaway. Well, so the point is that we are stuck with certain cosmological tensions, particularly Hubble tension is a significant challenge, and we don't have a solution yet. And the simple lambda CDM cosmology is not able to explain that. Then the recent tension is that we have observed the hint of dynamical dark energy in the DAISY results. And these are now questioning our assumption that we took in the standard model that the dark energy is constant. Now, what is even terrifying is that these findings are indicating that there could be a feature of phantom-like behavior of dark energy at early times. And then this further challenges us, because in general relativity, you cannot model these features. That means maybe you need to go beyond general relativity, which is one of the principle of lambda serium model, and maybe you need modified gravity. And then the later question comes that if there is modified gravity indeed, can we see the distinct signatures of such a theory on the growth of structures, and um, understand the effect of dark energy and gravity on cosmological scales? So yes, we can do that. Why? Because we are living in the times where we have a lot many ongoing and upcoming surveys. I've listed four of them here. So Dark Daisy and DES have actually completed their data, and they are now analyzing the data part. The observation is done, and we will have the final data release soon. And the Euclid mission is ongoing, and this LSST by Vera Rubin Observatory is about to start in this year itself. So the conclusion is that the nature of dark energy and gravity on cosmological scales is yet to be revealed, and these ongoing and upcoming projects are give us a large amount of data that we can study to understand deeply what is the true nature of dark energy. With this, I will thank you all for your patience.
Thank you, Yashi, for this very insightful talk, and it is very well articulated. And thank you very much. Now we have a
Yeah.
few questions in the chat box. Let me go through those one by one. Some of which you already addressed during the talk.
Okay.
One question was about the connection between the dark energy and the scale factor. Why the dark energy and how they are related.
So it's
So
related. Yeah. So I think it
I
is
think you already
related
answered
by
that
the
question.
this. Yeah. Yes. Exactly. Yeah. So it's like it's a scale factor is given is related to the expansion rate, and the dark energy controls how the expansion rate would actually go. So that is how we say the relation between scale factor and dark energy. Yes.
Okay, another question is how does a change from lambda CDM to W CDM changes the Einstein's field equation? So
So, so it's
yeah,
like now the Einstein field equation, instead of having, I mean, just go to the slide. Where is that slide? Yeah. Oh, okay. Just a minute. Yes, in this. Okay. Yeah. So in Einstein field equation, in the case of lambda, you have this lambda constant here. So now what will happen is that there will be no lambda, and whatever component is here is will be incorporated in this energy momentum tensor. So it's like instead of having matter radiation, so it's like if you see the equations, how Einstein equation will be transformed now. So you have matter and radiation, but for dark energy, in case of lambda, you just have a constant. Now what will happen? You will have some other term which would also evolve with redshift if the dark energy is dynamical. This is how it will appear. Yeah.
okay. Another question is can you briefly talk about phantom crossing? I also want to add a bit to that question because it is not just phantom crossing you are mentioning, it is also a singular equation of state appearing in your particular model.
Yes, this is in a
So
particular model. Okay.
there
Yeah.
is phantom crossing as well as negative dark energy in your
Right, right,
picture.
right,
So
right.
maybe you can comment about both.
Both of them. Yeah. So I'll start with the phantom crossing. So what is phantom crossing? It just means any transition uh, in equation of state between phantom and non-phantom regime. For example, if you see here in this plot, how W evolves with redshift, this is for the from the DAISY data for the best fit W naught WA model. So you see that at high redshifts, that is on the very right, the equation of state was less than -1. This -1 line here is what is the case of constant lambda. Now you see that equation of state evolves. It was initially less than -1, and it crosses this -1 and becomes less than -1 at present time. So z equals to 0 is present time. So this is what is referred to as a phantom crossing. Phantom crossing means equation of state was somewhere phantom in some epoch, and it has now transits to non-phantom regime. So this is just phantom crossing. I hope that answers the question. Now, talking about this particular model that we explored, so this model had actually the feature of negative dark energy as well. And this is something that's why you see this numerical spike in the equation of state, which arises when the energy density actually transits from negative to positive. So dark energy density cannot be negative at present time. Why? Because this is the dominant component which constitutes which also leads to the accelerated expansion. So what people have seen that if this energy density was negative at some earlier times. Why earlier times? Because at that point dark energy was really insignificant. If you see how the different energy components evolved with time. So in the early universe, radiation and matter were the most dominant component. So even if dark energy was negative, it does not make much of the effect to the overall energy budget. So there are various models that have explored that if this dark energy was indeed negative at earlier times, it could resolve some other cosmological tensions as well. So this is what happens in this case, where this additional feature is because of negative dark energy density along with phantom crossing. Yep. Does
Okay,
that answer your
anyone?
question?
Yes, thank you, Yashi. Anyone has any other question? Feel free to ask right now, or you can type in the chat
I have a
box.
question, sir.
Okay,
Sure.
please
Madam,
go ahead, sir.
Madam,
Yeah.
I am asking this question at the risk of looking like silly, but I could not help it. See, the question comes because of, I mean, getting a motivation to find some analogy with Cooper pairing process. Here you talked about baryons getting coupled with photon. If
Yes.
I'm not sounding silly, my question is, see, Cooper pairing in fact comes through uh, one electron interacting
Hmm.
through a somewhat distant electron within condensed matter, within condensed
Hmm.
matter through
Hmm.
photon. Sorry,
Hmm.
phonon. I'm sorry, phonon.
Hmm.
Here you talked about matter getting baryon getting coupled with photon.
Hmm.
Is there any such thing like a pairing, like Cooper pairing between?
I think this interaction is very similar to like you have a dense universe and they are interacting via Thomson scattering. Just as it is a scattering interaction that we have in between them, the baryons and the photons. And once the universe is expanding, this scattering will slow down because the photons have the tendency to free stream. It was just when the universe was very bound to be really small and dense that they were interacting with the baryons with these scattering. So I think it in terms of this is scattering between them. So,
Okay. And thanks for the talk. Madam, you appear to have prepared well for this talk. Thanks for giving a wonderful talk,
thank
well
you.
organized. Thank you.
Thank you. Thank you so much.
Okay, any other questions? If not, let me ask one final question to you, Yashi. Your
Sure.
dark energy equation of state also
Hmm.
tends to have a tracking behavior. Um,
Mm-hmm. Hmm.
so it lies in the phantom regime, but it in the past it settled down to zero. And I presume if you
Yes.
extend the redshift past to
Yeah.
earlier one, it also goes to 1/3. So how do you
Yeah.
explain this tracking behavior of this particular
So this
model?
is why the choice of the coupling functions, and it's not very close to zero. It looks like because of this numerical spike, which is large in amplitude, but it is something non-zero, and that is just because arising because of a negative dark energy density at those time. Pressure is always negative. It's the dark energy density whose amplitude actually varies, and that depends on the interactions that we have introduced in our model to get that negative dark energy feature which actually controls the amplitude of this equation of state. And at
So
present
the
times, it resides in the phantom regime actually. If you see in this subplot where you see that the present equation of state is phantom, and this is again arising because of the setup that we have worked with. So there are some self interactions of the scalar field which actually lead to a phantom kind of behavior of equation of state at very late times. If those interactions were absent, this would indeed do a phantom crossing and go to a quintessence type of equation of state at present time. But because of those self interactions, the way we have designed this, it resides in the phantom regime and gives a large value of H naught as you see in the first plot.
Okay, so the H naught, higher value of H naught is mostly due to the equational state between redshift 0 and 4 and not um, influenced by higher redshift value.
You can say that. That's why it reconciles with the PAO observations. You need to get this feature where the expansion rate actually lags behind lambda CDM at some redshift of the BAO, and then crosses to go to a large value of H naught. And these requirements are such that you don't disturb the angular diameter distances to the BAO by introducing some non-trivial dynamics as well as the CMB. So yes,
Okay.
yeah.
So in this picture of modified gravities, all these instabilities would somehow will be accommodated, like null energy condition violation.
Yes. So yeah, so these modified gravity theories give you immense phenomenology to like model these phantom behavior in terms of effective equation of state rather than the true equation of state in GR, which would violate certain energy conditions. So yes.
Okay.
In the chat box, there is one Manoharan. He had put up a graph. Is he wanting to tell us something? Will he be allowed to elaborate on
Yeah,
what?
I think that question was already answered, sir. And one last comment was whether we will be able to get these slides. So we are recording this whole video and we will be putting them on the KTPI YouTube channel.
Okay.
So I think we can see the slides in the YouTube video itself. So
Sure.
if there are
Sure.
no more further questions, I think there are no other questions. So, Yashi, thank you very much for joining us today and for giving us such a very well structured talk for us and taking us deep into dynamical dark energy and more. So, thank you very much, Yashi, once again, and we will see you on the next KTPI talk. Thank you, everyone,
Okay.
for joining.
Thank you. Thank you.
Thank you, Yashi.
Okay.